natural log of y equals limit n goes to infinity times n, or n times natural log of n plus, or n over n plus 1. Now what? What happens as n goes to infinity? This goes where? Infinity. And then this goes to, let's see, we said that goes to 1. Natural log of 1 is 0. So that's still an indeterminate form, but this time, this is like on your test. This was like the n squared times the sine of 1 over n squared. That problem on the test is this form. And so you have to take one and drop one, right? So I'm going to drop the n down, save myself some time. Just going to drop it down like this. And now I do L'Hopital. So the left side's natural log y. By L'Hopital's rule, I have limit n goes to infinity. All right, now I take derivative of this, right? Yeah? So what is the derivative of natural log of something? 1 over that, right? What's 1 over that fraction? It's that fraction flipped over, isn't it? So isn't this n plus 1 over n? That's the derivative of natural log of this. And then times derivative of what's inside. What's derivative of what's inside there? Quotient rule? Derivative of the top times the bottom minus derivative of the bottom, which is 1 times the top, all over n plus 1 squared. Is this looking like a kind of a disaster or no? Split. So what about the bottom? What's derivative of the bottom? Negative 1 over n squared. Y'all with me? I feel like I've lost you here.
It's repetitive.
Okay, but do you understand what I'm doing? Yeah? It doesn't look very nice, does it? Let me try and clean it up a little bit. I have natural log y, which is the left side. Limit n goes to infinity. And then this piece is n plus 1 over n times, what does this clean up to be right here? Is it n? It's 1 over n plus 1 squared, right? Look, n plus 1 minus n, right, is 1 over this. So I have 1 over n plus 1 squared, and then all of that over negative 1 over n squared. What can I do now? I can cancel out one of the n plus 1s, right there. What can I do with that negative 1 over n squared on the bottom? Flip it up, and it becomes n squared on top and negative 1 on the bottom like this. I can cancel one of the n's. What's left? Jeez. Natural log y equals limit n goes to infinity. What's on top still? Just 1 n, right? One of these n's. And on the bottom, what's still there? N plus 1 and then a negative, right? So negative n plus 1. Now let n go to infinity. Infinity over infinity? Yeah. L'Hopital 1 time. And what do you get? 1. With that negative, though. Negative 1. Yes? Okay. So hold on. We're almost there. Oh, we're almost there. Natural log of y equals, by L'Hopital's rule, the right side you told me was what? Negative 1? We wanted to know what y was, not natural log of y. So we come back and we put e on both sides. E to the natural log y equals e to the negative 1. So y is equal to e to the negative 1, which is the same as 1 over e. and e is bigger than 1. So let's go back all the way now to my ratio test. My ratio test had absolute value limit as n went to infinity of the factorial's canceled. What did I have? The n plus 1's canceled. Oh, I remember. It was n over n plus 1 to the n. Sorry. That's where we were, right? Right? Is that what we had? Yes? That's where we were in the ratio test. And we said, oh, crap, we're going to have to go do that somewhere else. And we just found out that that turns out to be 1 over e. So this is going to be 1 over e. I don't need the absolute value, but I'll keep it there. And is that less than 1? Absolutely. What does that mean? Therefore, sum n equals 1 to infinity of n factorial over n to the n converges. That's a pretty tough first example for ratio test.
You don't have to say, unless you were going to say that's the values, you don't have to say absolutely converges?
No, because it wasn't an alternating series. If it were alternating, then we would start talking about that, yes.
That's just because the absolute value is only there for its absolute.
That's right. The absolute value is only there. Oh, wait. The absolute value is what?
Only there for the alternating series.
Mm-hmm. Yes. 3 right into the fire on that one. Maybe we should do another one that's not so difficult. Maybe I should have done that first. This one's going to seem like cake now, hopefully. Sum n equals 1 to infinity of n factorial over 2n plus 3 factorial. You ready? Here we go, ratio test. Limit, n goes to infinity, absolute value. Okay, this with n plus 1 plugged in, right? So let's be real careful with this. It's n plus 1 factorial, yes, over 2n plus 5 factorial. N plus 1 goes right there, right? The 2 hits it and becomes 2n plus 2. So it's in parentheses and n plus 1 right there. 2 goes to both. The look on your face, Christy. If I plug n plus 1 in the bottom, that's what I plug in, right? The 2 goes through to each one. Then you get plus 5. Yes? And then over this without it in there, right? This without n plus 1, just n. And that's going to go underneath this, right? And then it's going to flip, isn't it? And that's pretty much going to happen every single time. So what I'll start doing is I'll start writing it flipped over already. Okay, so what is a sub n flipped here? 2n plus 3 factorial, and on the bottom, n factorial. Got it? Yes or no? Yeah. A sub n plus 1 over a sub n, flip a sub n, and bring it up. Now what are we going to do? Start peeling some factorials off, right? This n plus 1 factorial can be rewritten as n plus 1 times n factorial, right? And that'll kill this guy off. And then the 2n plus 5 factorial and the 2n plus 3 factorial. Which one should I start peeling? The 2n plus 5, because if I start peeling off this one, I'll eventually get to this, won't I? And remember what we're doing is we're peeling one off of each of these. So it's going to be 2n plus 5, and then what? 2n plus 4, then 2n plus 3, and then it keeps going, doesn't it? But at this point, I can do the factorial. And look at all the great cancellation I'm going to get. This, 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 this. And all you're left with, at the end of all that, is the limit as n goes to infinity of n plus 1 was the only thing left on top. And on the bottom, 2n plus 5 times 2n plus 4. And you have a linear expression over a quadratic, right? Like if you multiply these out, and then you could do L'Hopital's rule. It would be pretty clean L'Hopital's rule. Do you all know what I'm saying or not? I think that's the correct expansion of the bottom. 4n squared, 8n, 10n, 20. So there's the expansion of the bottom. Now L'Hopital one time, L'Hopital, right, is going to give us a 1 on top and what? Yep, 8n on the bottom, and then let n go to infinity. This thing goes to what? To 0, which is less than 1. So, converges.
I have a question.
Yes.
I have a friend in Cal 1.
Okay.
He told me that they don't learn L'Hopital. So
Mhm.
how do they do this when they come to Cal 2? Do they learn L'Hopital?
I don't know.
We like had to memorize a lot of weird stuff.
Yeah. It's pretty easy to pick up, though, right? I mean, it's not too bad to pick up, but I don't know. I mean, if you hadn't seen it,
Can't be done without L'Hopital.
what, can't do this one? Wait,
Like-
this right here without L'Hopital? You can do this one without
I
L'Hopital.
don't know, like we use L'Hopital a lot.
Yeah.
For all the tests and all that.
Yeah,
If you don't know L'Hopital, then not.
I'm sorry for you. I don't know. I don't know what to say. There are ways to do a lot of limits algebraically with some very clever use of algebra and some very tough algebra. But, you know, it's for the same reason we have wheels on cars, you know? Like, there's a reason why we use a wheel. It makes it a little easier, right, to move a car if you have wheels instead of boxes or something, you know? I mean, like, yes, there is some value in learning it algebraically, but then you are limited by that too. Because there are things you cannot do without L'Hopital's rule. Yeah, so, but they'll probably see it in Cal 2. All right, next test, root test. We're going to get plenty of practice with the ratio test. Root test, one example of root test, not used very often. Root test says that if you're given some series, then if the limit as n goes to infinity. So it's another one of these things where we're going to do a limit like we did with the ratio test. And we do the nth root of the absolute value of a sub n. If that equals L, all right, so we compute this thing, and it's the same conclusion. If L is less than 1, converge. L is greater than 1, diverge. L equals 1, fail. Why do they call the ratio test the ratio test? Well, because it was the ratio, wasn't it? It was a ratio of a sub n plus 1 over a sub n. They call the root test because it's the nth root of the sequence, the absolute value of the sequence. What does it say in your notes as far as in the comments for this test?
Useful if a sub n involves nth powers, if a sub n is greater than 0 for every n, disregard the
That's right. So this is very useful if you have nth powers. Now, an example of this would be sum n equals 1 to infinity of 5n plus 1 over 11n minus 1 to the n. I'm not saying right now that you can't do this with ratio test. You probably could do this with ratio test. But it would get a little ugly with ratio test where? When you plug in the n plus 1, right in there, right, you'd have to distribute out and n plus 1 in here, and it might get a little ugly. The power of the root test is that it allows you to take the nth root of whatever you're looking at. And do you see what happens if I take the nth root of something to the nth power? It just goes away, doesn't it? So what I'm going to do here is the root test. I'm going to take the limit as n goes to infinity of the nth root of the absolute value of this. So I don't need the absolute value because that's already a positive. And what happens there?
Is that next to, is that 11n?
That's an 11, yes. 11, yeah. Does it look like natural log?
Yeah.
Sorry. Sorry about that. Don't want to change it to a different number or something?
It's too late now.
Too late, okay. That's 11. You don't because this is always a positive number, right? That's positive. If n's 1 or bigger, that's positive, and then raise it to power, it should still be positive. So, isn't that nice? Look at that. Isn't that nice? The root kills off the power, and now you just need the limit of this. And what's the limit of this? Infinity over infinity, L'Hopital's rule. What do you get? 5/11ths. See, look, on a test, I mean, at this point, we're Cal 2, we're coming towards the end of Cal 2. I would not expect you to show me that you use L'Hopital's rule to get to this. I mean, that should almost, L'Hopital's rule on this should almost be just a mental computation now, right? Derivative of the top is 5, derivative of the bottom is 11, 5/11ths, done. Now, you could tell me what you did by doing that. So what's our conclusion here? It converges because this is less than 1, right? So it converges. That converges. That's kind of weird because you would think maybe that would diverge because that's a big, you know, that gets bigger and bigger. Just like geometric. Yeah, that's, the thing is, look, if I gave you this, if I did 5/11ths to the n and I told you that was a series, you would tell me that's a geometric series, wouldn't you? And it would converge because r is 5/11ths, which is less than 1, right? So it would converge. This is almost geometric, except for this is not a constant, right? But as n gets bigger, it gets closer to what? 5/11ths. So this is basically a geometric series, except we can't do we can't figure out what it adds up to. Can we do what? Maybe. Might be able to. But now, in retrospect, now you have the root test. You wouldn't probably want to do a comparison because this works so clean. All right. One last thing. Alternating series estimation theorem. Suppose you have an alternating series which converges. Not all alternating series converge. Everyone understand that I mean an alternating series here? Then it adds up to be a number, doesn't it? That's what that means. Then we can call the sum S. So in other words, S is whatever that adds up to be, right? But the problem is we would have to add up all of them forever, wouldn't we? And that's impossible. We would always have to stop somewhere in the sum on a computer or on a calculator, wouldn't we? If we actually wanted to try and figure out what it adds up to be, eventually you'd have to stop. This theorem says that if you take the sum n equals 1, and let's use k up here, of -1 the n, that would be the sum of the first k pieces, wouldn't it? Wouldn't that be the first k? So it would be plug in 1, then plug in 2, then plug in 3, and stop at k, wouldn't it? So we'll call this S sub k. It's the kth partial sum. Kth partial sum. What? No? Why?
Like someone wrote that on a paper, like a published paper or whatever.
What? The k? I've used this already. The nth partial sum. We used it before.
That's any of
Yeah, that's n. That's
Oh, it's a dummy variable. It can be anything. I could have said m and called it the nth partial sum. Just where I'm stopping is the partial.
funny. Like,
I could call it the pth partial sum. That'd be kind of cool. The qth,
yeah.
the zth, whatever you want, man. I mean, the kth partial sum. It's the sum of the first k pieces, right? Y'all don't like that?
No, I don't like that at all.
Okay. All right. So we have the true sum, which is adding them all up forever, right? We have the kth partial sum, which is the sum of the first k pieces, right? This theorem says this. If we call this the kth partial sum, then here's the result. Then the absolute value of S minus S sub k which is the true sum minus our approximation, which is stopping somewhere, right? That difference, the difference between our partial sum answer and the true answer must be less than b sub n plus 1. What? What's b sub n? It's, look back in there. Isn't b sub n just this piece right here? You have the -1 in front. The b sub n is here. That b sub k plus 1. Sorry, k plus 1. Sorry, b sub k plus 1. The difference between our partial sum and the true answer is always less than plugging k, which is where we're stopping, plugging k plus 1 into that little formula right there. And that's amazing.
Oh yeah, that makes total sense.
I'm going to show you. I'm going to show you. But this is an amazing theorem because it gives us a bound on the error. All right? So what we do is we call this something. We call it R sub k, absolute value, which is basically our error. And the capital R stands for like remainder. It's what remains. All right, let me see if I can show you this, all right, in action. You ready? All right. Let's start with this. Find sum. All right, so I'm going to give you a very special series right now. Hopefully you'll recognize it. Geometric series. Since it's a geometric series, we can find the sum. Do you remember when I handed out the test and I coughed real loud? I was like, sum! Do you remember that? When I was handing out the test, telling you last class, and I said, and on this number, find the sum. Do you remember me coughing real loud? Right when I got to the word sum?
That means that you
I was trying to remind you sum meant it could only be telescopic or geometric. Anyway, okay. This is a geometric series, right? What's A? What's R? What's A? What's R? A is 1. R is negative 1/2. Is the absolute value of R less than 1? Yes. Therefore, it what? Converges, right? This converges. Agreed? Agreed. Yes, yes, yes. Okay. Sorry.
I'm confused where you got your A from.
There's 1 right there.
Oh, okay. Oh, yeah,
Right.
never mind. Sorry.
You good?
Yeah, sorry.
Now, watch this. I'm going to do a little tweak to this. Does everybody agree that's the same exact series? All I did was I took the negative in here and wrote it as like negative 1 times 1/2, and then I broke it into 2 pieces to be this. Yeah? Yes? Okay. This is an alternating series, isn't it? This piece is B sub n. Y'all agree with that part? What does the alternating series estimation theorem tell us? That the difference between the sum and S sub k should be less than B sub k plus 1, right? That's what it says. Did we find the sum? For this series, we can find it, can't we? It's A over 1 minus R. Should we do that now? Let's find the sum of this series. S for us would be A over 1 minus R was what? Negative 1/2. So this is 1 over 1 plus 1/2, which is 1 over 3/2, which is 2/3. So according to the estimation theorem, we already know what this adds up to be. A lot of times you won't know this, okay? But just to show you how it works, we know that this is 2/3, right? What I know is that the difference between that and S sub k should be less than B sub k plus 1. Somebody give me a k to stop at, a partial sum. And let's not do crazy. And never mind, don't give me a k, I'll give me a k, all right? I'm going to just pick a k and see what that k does. So I'm going to do 1, then 2. Let's go to 3. Let's let k be 3, okay? Let's let k be 3. Let k equal 3. So when I take a look at my original series, if I were to stop at 3, right? If I were to stop at 3 and just add up the first 3, what would I get? Let's see it. Plug in 1, what do you get? Negative 1/2 to the 0, which is 1. Plus, now plug in 2. What do you get when you plug in 2? A 1. So negative 1/2 here? Yeah? And then plug in 3. And you get what? What's negative 1/2 squared? 1/4? So let's add those up. What's 1 minus 1/2 plus 1/4? 3/4, right? 3/4? Yeah. So according to the estimation theorem, the true answer minus the kth partial sum, 3/4, that should always be smaller than what? B sub k plus 1. That means if I just look at k, k, which is 3, right? And I look at b sub n. What was b sub n? Everyone has to go back and look at the way I wrote b sub n a second ago. What was b sub n? It was 1/2 to the n minus 1. If I ask you now what's b sub k plus 1, I'm really doing b sub what? K plus 1. B sub 4. So if I do b sub 4 here, I put a 4 into that, and I get what? 1/2 cubed? 1/8? According to this theorem, I'm guaranteed that this is going to be less than 1/8. Should we check it? Should we check to see if this is true? What is this? Put these two fractions together. 8 minus 9 over 12. This is 1/12. Negative, but an absolute value, yes. Is the absolute value of negative 1/12 less than 1/8? Yes. Now, you might be sitting there going, well, who cares, right? Who gives a rat's ass about this, right? I'm reading your mind. Here's why. This was just to show you how the theorem works. This problem that I gave you, though, we knew what the sum was, didn't we? Like, we knew what 2/3 was. I was just showing you the theorem worked, so you should feel good about it. But now let's see how it actually would work with something we don't know about. How about this right here? Does that converge or diverge? Converges because it's an alternating harmonic, right? We looked at that like 3 or 4 times today. We don't know what it converges to, do we? Right? We don't? You agree? We do not know what that converges to, but we do know it converges. I would like for you to tell me within what is this sum within 0.000001 tolerance. Tolerance? A and C? Yes. We know it converges, right? But we don't know what it converges to? But I'm asking you to tell me what it converges to within 1/10, 100, 1,000, 10,000, within a millionth. Give me the sum of that within, you can be off by 1/1,000,000th, okay? That's okay with me if you're off by 1/1,000,000th. But I want you to be that close to the true answer. Understand what you're trying to do? So what you would do is this. You would try and figure out how far out you need to go. How much of a sum do you need to use here? The question is, at what k do I need to stop in order to get within that much? Right? Yeah? I'm going to rewrite it like that. This piece right here is our b sub n, isn't it? What does the estimation theorem tell us? It says that the true sum, which we have no freaking idea what it is, minus our approximation, which is s sub k, which is this, has to be less than what? B sub k plus 1. But we want that to be less than what? How close do we want to be? 1/1,000,000th. 5 ones, or 5 zeros and 1. Right? Understand? So, you give me a k that when I plug it into b sub n right here, it's smaller than 1/1,000,000th. So everyone tell me what b sub k is right now. This is b sub n. What's b sub k plus 1? 1 over k plus 1, right? I need 1 over k plus 1 to be less than 1 millionth, right? That's what I need. So how big does k need to be? I need 1 over k plus 1 to be less than 0.0000. Well, let's do it this way. 1 over a million. That's what the right side is, right? That's what I need. K's what? K's got to be bigger than 9, 9, 9, 9, 9, 9. I'd have to go out to the 999,999th sum to get that close to that tolerance. Now, I wouldn't want to do it, but that's if I'm in a computer and I need that tolerance. If I'm going to go that close to the true sum, I'm actually going to have to add up the first almost million of those to make it get that close to the true sum. Understand that? Let me do one more in the last 3 minutes. Let's look at another convergent series. Oh, I can't add those up, so I can't tell you what the sum is. Sorry. I could get a computer to do it. I'll give you one that goes faster, that converges faster. How about this one? Sum -1 to the n times 1 over n to the 5th power. I would like for us to find this sum within, let's not go crazy with the millionth, let's just go within 0.0003. So that's within within 3 10,000ths. See if we can set this up a little faster now, right? We're trying to set up this sum. This is convergent, by the way, isn't it? Why is that convergent? It's alternating, right? So we do an alternating series test. This piece goes to 0, and you could show it's decreasing. That's one way. What's another way? Take the absolute value of it, and that's a p-series. Since that converges, that one converges. Yes? So either way, this is convergent. So we have to have that, or else there's no sense in us doing this. The sum to k, right, is what we're trying to look at. And we know that the true sum minus s sub k must be less than b sub k plus 1, which must be less than, in order for this to work, 3 over 10,000, right? What is b sub k plus 1? 1 over k plus 1 to the 5th must be less than 3 over 10,000. And here's where you could just get your calculator out and just try some values. And I think I might stick with this. Let me try k being 1. What's k being 1? What happens if I let k be 1? I get 1 over, 2 to the 5th? What's 1 divided by 2 to the 5th? 1 divided by 2 to the 5th is 0.03125. All right? Is that number smaller than this number? No. So taking the first number is not enough. So let me do k is 2. If k is 2, this is 1 over 3 to the 5th. Y'all with me? So if k is 2, I get 1 over 3 to the 5th, which is 0.004115. Is that smaller than this? No. So now you let k be 3, which will be 1 over 4 to the 5th. So k equals 3. If k was 3, we get 1 over 4 to the 5th, which is 0.00097. Still not smaller, right? The next one will work. K is 4. which is 1 over 5 to the 5th, which is 0.000, I don't know, I'm getting 3.2. That's bigger than this, right? A little bit bigger. Yes? Okay, I'll change the problem to 4. There. Okay, so the first 4, right? If k is 4, I know I'm out of time, but I want you to appreciate what we can do now. I can actually take this sum right here to 4. If I just go to 4 and I start plugging in, what happens? N is 1, I get negative 1 times 1, right, if n is 1. Plus, now plug in 2, that's squared, so it's positive, 1 over 2 to the 5th. The next one will be minus, won't it? And it's 1 over 3 to the 5th. And then plus 1 over, what, 4 to the 5th? That's the sum of the first 4, isn't it? Okay, if I add these up right now, I guarantee you my answer is within 3/10,000ths of the true sum. I'm off a little bit, but I can go, if you want me to be closer to the true answer, I will just go a little further out. Do you all see that? And that's the way your computers work when they're, you get these decimal points at the end. At some point your computer has to stop, right? So these are like built-in functions, and they say, look, I'm going to go until a built-in tolerance and stop, and that'll be what I return to the user as the answer. All right, I'm out of time. I'll send an email out for homework. Well, I have them right here. Who has a book I can borrow real quick? Not all at one time, please. I'll send the email out. Y'all get out of here.